Boker Tov. How are you? Good. I'm going to talk about some version of symmetric computation. I don't know much about it. I will say what I know. The reason I'm talking about it is a paper that I will mention later on that I did not write. So if you have questions or if I'm saying something wrong or something like this, just say. So this is a very high-level slide. In algebraic complexity, there is some polynomial, and we want to understand its computational complexity, like what is the formula size or what is the circuit size. And this turns out to be difficult for us for now. So we try to answer simpler questions, like there are restricted models of computation, and we can try to understand them first. Okay, good. So this is the high level, what we want to understand. And then Valiant had a very nice idea that we can remove from the question the graph, the topology of the computation. Ignore it, which is very nice. We don't need to think about graphs. And the way he did it is like this. He proved two things in this context. One is that if a polynomial can be computed by a formula, an algebraic formula of a certain size, then this polynomial can be written as the determinant of a matrix, where the size of the matrix is the size of the formula, and the entries in the matrix are affine functions in the variables. You know this theorem? Yes? So this is for formula, and so formula corresponds to determinant. He also proved a similar result for circuits, and circuits correspond to the permanent. It's the same statement, except it's permanent. And the star there means that he proved something even much stronger, not just for circuits, but for something more general than circuits. But it's not so important for now, so I'll keep it this way. You, okay? You know how to prove one, for example? One word, how do you prove it in one word? Induction, yes. How do you prove two? I don't have one word, how many words? Well, gadget, yes, one word. Yes. And you prove both of them in one word as? Valiant, yes. So, good. So now we remove the circuit. We have a different, somewhat maybe easier to phrase problem. Now we are given some polynomial f, and we want to know what is the minimum size of a matrix such that f is the determinant of this matrix. This is called the determinantal complexity of f. When I write determinantal in LaTeX, it always put this red thing below. So it's not a word in English, at least as far as LaTeX is concerned, like whatever editor I'm using. So this determinantal complexity is some analog of formula size, or of branching program size of a formula, of a polynomial. And we want to understand this number, which here there is no circuit, so it may be better to think about this type of question. Okay, so this is a difficult question. Again, so there is some approach that was suggested relatively recently to solving this problem. And specifically to showing that the determinantal complexity of the permanent is high. So what is this approach, at least the basic of this approach? We have this set of variables x, it's x1 to xn, and we can look on the vector space of all linear functions over this set of variables. I call it V. So we can take the group of matrices, invertible matrices over V. This acts on V by just you multiply a vector by a matrix. And so this vector space, this group also acts on the space of polynomials. You can take a polynomial and change the variables according to the matrix. So you know all of this, right? Yes, good. Thank you. And then you can look for every single polynomial, what is this set of matrices that fixes this polynomial, or the group of matrices that fixes this polynomial. In that set of matrices, when they act on this polynomial, the polynomial remains the same. And this one there, where you can see half of it, is that sometimes this is defined in a projective way. I will not put so much emphasis about this difference. So this is the definition I will use. It's okay? Yes? Okay. So what is this approach, sort of the very high-level idea? Is that because the stabilizer of the permanent is so different than the stabilizer of the determinant, then the determinantal complexity of the permanent should be high. This is very high-level statement. And this is also a difficult thing to understand. We don't understand it. So again, in this context, we can try to understand simpler questions first. This is, I think, a reasonable thing to do.
G that should be a subgroup of G perm.
So it depends in which dimensions they. So I didn't write what is the number of variables, but or maybe I did. What is the question?
Like you permute the variables, right?
You are asking what is G of the permanent, for example? The permanent is a, yeah, you can permute the rows, the columns of the matrix. This keeps the permanent at ease. You can permute the columns of the permanent. This also keeps the permanent. And there is this, you can multiply with a diagonal matrix so that the product of the diagonal is 1. This also keeps the permanent as is. And this is everything. Sorry, yes. You can also do transpose a matrix, and it also keeps the permanent. So this is the G of the permanent. And G of the determinant is very different. It's more continuous in some way. You know what is G of the determinant? Or did you see this? I sort of assumed you saw something about it.
Isn't it like a subgroup of G perm, like whatever permutation you can apply on that?
No, like for example, if you swap two rows in the permanent doesn't change, but the determinant will be a minus sign.
Yeah, so it won't be in G that operator, but it will be in G perm.
Yeah, I guess there is also this thing of how large the determinant is and how large the permanent is.
So I will. Yeah, there is this issue of making the same number of variables, which is related, I guess, to your talk about. But yeah, so I don't want to. This is very high level for now. I will be more. So there are two groups: the stabilizers of permanent and the stabilizers of determinant. It turns out that these characterize the determinant of permanent, meaning that any polynomial that is fixed by G permanent is the permanent, and every polynomial that is fixed by G determinant is the determinant, up to this projective issue that I ignore for now. So this is a very strong property of permanent and determinant, or very weak property, yeah, it depends, very special property. So I summarize this whole approach in this slide. It's, of course, very limited, not deep what I'm saying. But so what is to remember from this? Every polynomial has a stabilizer. The stabilizer is the symmetries of the polynomial. This is a way to think about it. The polynomial has some symmetries. This is the stabilizer. And understanding this stabilizer is related to understanding the determinantal complexity of the polynomial. Okay? Good. So as the last point I sort of made is that we can try to ask simpler questions, like restricted type of computations of this sort. So we have this equality. F is equal to the determinant of some matrix. And we can think about M now as the thing that computes. The structure of M is the computation, the device that is doing the computation. And we can ask, how is this M, how does this M correspond to the symmetries of F? Yes? Okay. So Landsberg and Ressayre gave a definition that captures this idea. We want a computational device that computes F and respects its symmetries. How do you define this? So first, let's look a little bit about this equality. We can take a matrix H, and we can act with it on F, on the left-hand side of this equality, and we can also act on it on the right-hand side of this equality, and this moves actually the action to inside. Yeah, the variables are written inside the determinant. So when you act on the variables, you act inside the polynomial. This equality is still true if F is a stabilizer of, so this equality is always true. Yes, but if if H is in the stabilizer, then the whole thing is F again, because H of F is F. So instead of this equality that is always true, we can look inside on what H does to the device itself, to M. This is what they suggested. We have this device M. F has some symmetries. Look if the device respects the symmetries. How you define it? So here is the way they define it. We have this matrix M. This matrix has every entry is an affine map in X. So it's some linear function plus a constant. This is an affine map. I write it as A plus B. And we can look for this specific matrix, whose determinant is F, on all the matrices that fix the determinant. This is G is a larger matrix. It's then the number of variables, the size of G is the size of the determinant, the number of variables in the determinant. So we can look on the set of matrices that fixes the determinant and also fixes M, fixes the device. What does it mean to fix the device? It means that when we act on the linear part, we get the same matrix, and when we act on the constant part, we get the same matrix. Yeah. So G of M is the part of the thing that fixes the determinant that also fixes M. So it's the part of the symmetries of determinant that also works well with this specific device we have, this specific M. So now, when is the M, a matrix, a good or a symmetric representation? If for every symmetry of F, there is a symmetry of M such that H of M is G of M. Now H acts on the variables which is inside the matrix. G acts outside the matrix. It does linear operations of the matrix. Yes? So it's not the same action. H acts inside, G acts outside. It's clear what I'm saying? Yes? No. So, so let's look on this matrix M. H is acts on the variable. So every entry is replaced by something like H of X, every individual entry. G is a map that is a map like this. Or maybe this is not the most important property of G. G takes, it has, if this is M by M, G is a M squared by M squared matrix that is allowed in every entry of G of M to write a linear combination of these M squared things. So it acts from the outside. Or at least this is how I think about it, I'm not sure. So H of M is from the inside, G of M is from the outside, and we want that for everything that fixes F that can act from the inside, there is a thing that fixes the determinant and acts from the outside that is the same. So it's a very abstract definition. We will see an example. I think it's very abstract. And the example, I think, is very convincing, at least for me.
Instead of the determinant, suppose we were interested in the computational device as being a projection of a permanent.
Mm-hmm.
Then the outside action is basically just the permutations of the rows or columns or transpose.
And you can also multiply by the torsion. Yes. Okay. And now you can define a different complexity measure. It's the minimum size of a device that respects the symmetries. The equivariant, this determinantal complexity of a polynomial, is the minimum size of the matrix that is an equivariant representation of the polynomial. So this is a new definition. This number is larger than it's not smaller than the previous definition because the devices are more restricted, so it's harder to compute. And in fact, I don't know, and I think they also don't know, if this is actually, if such a thing can compute any polynomial, if this number is finite. So I think this is a nice question to think about. Landsberg and Ressayre. It was written here. Yeah.
For polynomials without symmetries, it's just the same old thing.
Yeah. If F does not have symmetries, it's the same.
So for all those, of course, it's less than.
Yeah. So for a generic polynomial, it's the same. The interesting thing about all of these approaches is polynomials with symmetries. So maybe I will mention.
So in particular, all polynomials can be approximated by polynomials that have a finite ease, right? In a closure manner.
Yes.
columns have no symmetry, so their EDC is finite.
Oh, and everything can be approximated by
By determinant.
Yeah, so this thing is not very stable in the like like Zariski thing, Zariski topology or whatever. Or any other topology. What?
In the definition of EDC, what is precisely the S there? I missed.
So S, yeah, it's not written here. It was. No, where is it? Here. S is the size of a matrix M. Yeah. Okay, so this is a nice definition, I think, and I think it's worth understanding it. At least this seems like a nice question to me. But they also prove some theorems which are very interesting. This is another reason. It's
What was the, I'm sorry,
Yeah.
what is
Don't be sorry. It's
difference
okay.
between DC and EDC? It looks like DC, the definition, I'm sorry.
So DC, we just want the determinant of M to be F. EDC, we want the determinant of M to be F, and we want that M will respect the symmetries of F. We add an extra condition. So they prove, they calculate exactly this complexity of the permanent, over the complex numbers, which is a very nice statement. Here is an exponential lower bound on something. And they also show that this complexity of this very simple polynomial is n+1, exactly. And I want to talk about the second point, because I think it demonstrates some things that are actually understandable. In this definition, it's n. It's the same representation. They have some other version, which maybe you know more about. Never mind. Yeah, you're right. Yes. So this is what I want to talk about from here until the end of my talk. We have this very, very simple polynomial. The group of its symmetries is this group. Yeah, it's the thing, the matrices that cancel when you do inner product. So maybe one thing that took me maybe some time to notice that this is not, this is, let's say, complex number. This is not unitary group. There is no conjugate here. It's just transposition. Yeah. So this is the polynomial. This is the stabilizer of this polynomial. And here are some properties of it, which I find nice. So the first is the determinantal complexity over the complex numbers is actually not n+1, is over 2. Yes? So this is not the thing. This. I will not use it. So the equivariant complexity is n. If we remove the equivariance, it becomes n over 2. So symmetry harms the computation, makes it harder to compute. This is one statement. And so this is 1 and 2. And another statement is interesting, at least to me, is that over the real numbers, the determinantal complexity without the equivariance is again n+1. So there is a difference between fields as well. So over the complex number, the determinantal complexity is n over 2. Over the real numbers, it's n, which is also something subtle is going on. The field matters somehow. So I want to talk about these 3 items. Which no. Yeah, you are right. It's for maybe 3 or 4. Yeah. Yes, we will see it. I will explain why it's true. Of this polynomial, I'm not sure. Easy is so this is the 2 norm over the real numbers. Over the complex number, it's a polynomial. It's analytic. So. Yeah. So I don't think it's hard, but I didn't think about it much. Okay, so let's start with an upper bound. The upper bound is a construction. Here is the upper bound. If you compute the determinant of this matrix, the matrix has 0 in the 1, 1 place, then minus x in the first row, y in the first column, and then the identity. Then the determinant of this matrix is the inner product between x and y as polynomials. Okay, this is very simple to verify. To think about, it would take me some time, I think. So this is the starting point, this equality. So here is, so for example, if you write x and x, you get q. If you replace y with x, you get q. So I want to say that this means that the equivariant complexity is at most n plus 1. The size of the matrix is n plus 1, so this is n plus 1. Why is this an equivariant representation? So this representation respects the symmetries of the polynomial we started with. Why is this true? So we take some matrix that fixes this polynomial, and when it acts on the matrix, this is what it does. It acts on the x and acts on the x. Okay? Now we need to find a matrix G that acts from the outside that fixes the determinant and does the same thing. So here is the action. We take the matrix M prime to a new matrix, which is M prime conjugated by this matrix. So just this operation. And you can verify that it's the same operation. It's not, there is nothing deep. But I think that for me, the interesting point is that this simple matrix computes this polynomial relatively efficiently and also respects its symmetries. So there is something in this definition. So this is, we concluded that the equivariant complexity of this polynomial is n plus 1, at most n plus 1. So specifically over the real numbers, the determinantal complexity is at most n plus 1, which is the upper bound. But over the complex numbers, we get a bound of n over 2. Why? Well, instead of x, we can write x1 plus i2. ix2, x3 plus ix4, and so forth, and x1 minus ix2, x3 minus ix4, and so forth. We just write it. This is formal polynomials. We just write it. So we replace the symbols by other symbols, and we get a sum of these things. This is a plus b times a minus b, which is a squared minus b squared. But because I squared is minus 1, we get the polynomial q. Okay, so this is a smaller representation that is achievable over the real numbers. You can't do this. There is no way to do this over the real numbers. So this is what I will show now. If you have a real number whose determinant is q, then the size of this matrix is at least n plus 1. So this is in contrast to this, here it's n over 2. So I will tell you the idea of this proof. The first idea is to say that M, this M, has a special form. What is this special form? You can write M as A plus B, but B is a diagonal matrix with 0 and then 1, 1, 1, 1, 1 on the diagonal. Okay? This property follows from derivatives of F, of Q, and the symmetries of the determinant. It's an exercise in this case. Okay? So if we have a matrix whose determinant is Q, then B, the constant matrix, has a very, very specific structure, this structure.
Just to be sure, A is a matrix of linear forms, right?
Yes, A is a matrix of linear forms. Yeah. Do you know how to prove it? No. Okay.
What is
Smooth? So there is a, you can do several definitions. Here, for example, it's very simple. If you take the, you take all partial derivatives, you get some function, n functions. You look on the, when are these functions 0? In this case, the n partial derivatives are just x1, x2, x3. So when is this 0? Just at 0. So this is smooth. In general, you need to count the codimension of something. Yeah, so this is the second step. So with A, your idea gives the +1 also. I will try to explain. So this is, I guess, what Amir meant. If you look on the first column of this matrix M, then this first column must contain a copy of V, in the sense that there should be n linearly independent linear functions. Why? Because otherwise there is an assignment to the variables that makes these linear functions 0, but the vector is non-zero. And over the real numbers, this cannot be, because Q is the norm. Then Q of x on one side is not 0, because it's Q at some non-zero point. And on the other side, we made a whole column of the determinant 0, which makes the determinant 0. So over the real numbers, this gives n, but because the diagonal has a 0 entry, this gives a +1. So, okay? Yes? Who understands where the +1 came from? That's pretty good. So we look on this matrix M, and we look on the first column of this matrix. The first entry in this matrix is 0 because of B. Now the other entries are some linear functions in X. There are some number of, this is S minus 1. The size of the matrix minus 1. Now, if this number is smaller than n, we can make all of these linear functions 0 with a non-zero assignment, which is a contradiction. So the number of linear functions is at least n, which means that S is at least n plus 1.
Yeah, it's again a question of the sum of cables. So you're saying that whenever, say, Aij is non-zero, then Bij has to be 0?
No, it could be, we just took the constant and put them.
Yeah, but
on this.
Why is the first entry 0?
Because of A.
Sorry, I didn't write it here. So you're right. This is 0. This is 0. So it's part of A star. It's part of the A statement. Yeah, sorry. You're right. Yeah. You first prove that this is 0 in the same. Yes.
Sorry, so then clearly I understood it previously. But
So I will try to explain why this is 0. If this is not 0, what is written here? Say x1. But then you compute the determinant of this thing. When you compute the determinant, what does this multiply? It multiplies what is written in here. And what is written here contains I. So you will have some linear part. But Q does not have a linear part. Okay? Okay. So this is a proof sketch. So I will summarize it as first you deduce some structure on M. Then you use this structure of M. This does not work over C, as we saw before, because this is not a contradiction. The last statement is not a contradiction over complex numbers. I'm almost done, I think. How much time do I have? How much time do you want? I don't. I can. You can prove. 10 minutes. Wow. Which part? So, at least I hope I'm saying something correct. Say it's x1 here. Then you compute the determinant of the whole thing. So this multiplies the determinant of this matrix. The determinant of this matrix has a constant in it, because B is 1. B is 1. So here you have like some constant. But then you have x1 times a constant. This does not appear in X.
And it cannot cancel out.
the only linear term that you have in this matrix.
Because
Yeah, but yeah. Yes, so you need to.
0, 1.
So just assume that B is 0, 1, 1. Okay, you know that. So which means if you have to generate a linear term, you have to pick one linear polynomial and the rest have to be these ones. Right. There is just one choice.
Yeah,
This has to show that the LIs are non-zero.
no, if some of them are 0, then it's even.
Sorry, LIs are not they don't have constant.
Yeah, this is what the B stands for. B is all the constant in this matrix. All the constant in this matrix appear here. 1, 1, 1, 1, 1. So you need, it's not, I didn't say all the details, but it's, I think it's reasonable enough. So this means that over the real numbers, the previous representation is the best representation, this matrix.
So does this proof also leave the thing for complex numbers? Like now we can write L1 as L1 plus I times L1 prime, L2 plus I times L2 prime. So therefore S minus 1 becomes.
So I think the statement is that you look on the.
Now we have 2 S minus 1.
You look on this variety where Q is 0, and you are saying that there is some
Like I'm saying if S
subspace of dimension at least more than n over 2 that cuts it. Sorry, every subspace of dimension more than n over 2 cuts it. in like a non-zero place. And maybe what you said is a way to prove it, yes. Okay, so for now, we proved 2 upper bounds, a lower bound, and now the most difficult lower bound is about the equivariant representation. So now we have a matrix that respects the symmetry of this polynomial Q, and they prove that this must be a large matrix. The way they phrase it is there is some algebraic group here, and you write, you choose some maximum nilpotent group and do some things, and you use Maltsev theorem. So there is a lot of group theory abstract going on in their proof, which helps also for the determinant, this type of reasoning. I will not explain it. But the first step is the same as before. Same polynomial, it's all algebraic. There is nothing special about real or complex. Same statement. Second statement is now we have this restricted action. G of M has to respect the structure of the constant matrix B. This is the restricted part. Like this, what makes the model restricted. So the group that we should now find a copy of the symmetry of Q inside this G of M. This is what should happen. But this G of M is very restricted. It has a very special structure because it fixes the constant matrix B. It's not a general group. And it turns out that this specific structure sort of says that when G acts on a matrix M, what it does to the first column is just some linear transformation. So it doesn't move things from outside inside, just keeps this thing in place. So this means that in here again, there should be a copy of V. Yes? Because now we can, the symmetries of Q can move every x to every other x. So here you must have everything. If here it's written x1 in M, then it could be written x5 in H times M. And if this is not the case, so G of M cannot do it. G of M, if x5 is not written here, she cannot take x5 and put it here. Because this is what the structure means. So G of M only acts inside of this. So it cannot move x5 from here to here. But H can. So it must be that somewhere here there are n linearly independent things. Plus this one, it's n plus 1. Again, not very formal. But I hope you, so summarize of this slide. Use smoothness of F, take derivatives, compute something. Then study what does equivariance, what restriction does it give? And use, in general, decomposition theorems for algebraic groups. How does they compose? What can this group do? What can this group do? How does they work together? And all of this together shows you that there must be a lot of space in order to put the whole group in. Yeah.
Can you say what you said again on the NO2 representation? So why it doesn't respect the symmetries?
So it's exactly for this reason. So now say you want to write the G of Q acts, there is an issue with the camera, G of Q acts on the first column by just linear transformation of the first column. So in the first column, there will always be x1 minus ix2. Whatever thing G you act on, this thing will never be broken to x1. Yes, it makes sense? Okay, this is basically it. I will just... so here is my summary. First, this type of... this is a lot of algebra, like group theory, abstract algebra, but it gives some ways to define new notions of restricted models of computation. And this is worth understanding, I think. And in the specific definition they gave, they actually prove correct bounds, which is another indication of something. Another point that is interesting, I think, is that this type of reasoning can actually give algorithms to compute, say, permanent, like Ressayre formula. So you can you look on representation theory of Sn. This tells you something related to the determinant, to the permanent, sorry, and this translates to this Ressayre formula relatively abstractly, which is amazing, I think. So this structure gives you a way to compute things in a symmetric way. So Ressayre formula is actually not a good representation, but there is a similar, you know Ressayre formula? Some way to write the permanent. So there is a way to interpret this formula as coming from the group of permutations on n elements in some abstract way. You have a group, it gives you a formula, sort of, you use the group representation theory of this group, it gives you a formula, and this formula is almost Ressayre formula. So it's like completely abstract, and you get something concrete. So the determinant does not have this Sn. So I don't. Maybe you can approximate using this, but I don't know. So you don't have this nice representation theory. Or I don't know. It's related, but it's different. I don't think I understand it well enough to actually give you a good answer.
What is the idea behind the determinant? It's roughly the same, except that you have this group, you decompose it to a direct sum of other groups. Each must respect some part of the irreducible representation of Sn. But it's linear algebra, except very abstract one. I don't know. I don't know. I would guess not, but it's a guess.
You just asked him, how do you find this formula from the representation?
I didn't explain it, so yes.
So this structure on the matrix B,
The
fact that it's 0 diagonals, does this use the fact that you are looking at an EDC representation?
No, this is general, as long as the original polynomial is smooth, meaning that you look on the n partial derivatives, when there is 0, this thing is large. It has a codimension at least 5 or something like this.
So in particular, is it true for the permanent?
For permanent, it's true, yes. This is a von Zur-Gatten proof, this, I think.
In fact, this is true for any polynomial that vanishes on 0, right? I mean, in the sense that you can always assume that the constant matrix is a matrix of, it's a diagonal matrix that has at least 1 0 on the diagonal. And smoothness will tell you that it is exactly that.
Yes. And the last thing that maybe makes it less interesting, this model, is that it's not a computational, like maybe it's sometimes infinite. So if it's sometimes infinite, maybe it's not as interesting, maybe it is, I don't know. But it's a nice question. Is it always finite? Maybe it's maybe on the other side, if it's sometimes infinite, maybe it's easier to prove because it's like computability. This is not computable. This is relatively maybe easy compared to actually.
Did you consider EDC bar lower bounds for your
Bar meaning closure, like close enough. I didn't consider it for sure.
But closure will always be upper bounded by DC bar.
Yeah, could be low. Could be lower. He gets lower bounds for EDC, for his function, for his polynomial. EDC bar could be lower. I'm just wondering.
The point is that like you expect EDC bar to be about DC bar, and so proving lower bounds would still be required.
I don't know. I hope it was okay. Yes.
So, just wondering, do they also give other examples in the paper for upper bounds, like
Yeah, they have not symmetric. They have this Ryder formula for permanent. And there is also a related issue. I don't remember how they call it, something with R, ERDC. I don't remember what the R stands for. And then there are also some construction, and this is related to branching programs. And so these upper bounds are also interesting.
So, for example, iterated matrix product, do we know what the upper bound of this model?
They don't write it. I didn't think about it, so I guess it's no.
Because ERDC is the one where you only respect the row symmetries.
No, it's insisting that B has this form, of this form.
But don't you always get?
Only if the polynomial is smooth enough. So the determinant is not smooth enough, and then you have for example, the determinant is not smooth enough, and then you don't have this. And of course, we know that in the minimal representation of the determinant, there is no constant. It just so.
The lower bound that you showed for, or you said about permanent,
That they should
equivariant representation.
somewhere here.
Is it anything to specially do for permanent, or if I take any immanents,
Any?
any other characters, I can consider the immanent for it?
I don't know. But here they also have a construction. It's equality. So I don't know. I don't know.
Regarding iterative matrix modification, so is the invariant group just a conjugation even conjugations? Is it only because maybe the case that the reduction that you showed from IMN to that already respects this.
Possibly, yeah. So wondering.
Because you have blocks of the matrix and the 0 and 1s on the diagonal. They don't know.
There is a classification of Ayman by itself.
And is it just a conjugate conjugation?
Yeah, so I guess an interesting question would be if you could prove such a low bound for polynomial in VP, an interesting polynomial which has, an exponential lower bound.
So yeah, so another question that they ask is that they write it in a nice way. I think it's a nice sense of humor in a paper. They write something like this: is it true that E of DC is at most E of DC, where E is a polynomial? So they ask it as a question, which is what you asked.